Hello, everyone. I think today you have heard a lot about Hexagon, H3, etc. So next thing, I'm going to talk about how we are going to process the Hexagon data. Particularly, I'm going to focus on how we want to smooth the Hexagon data, and then how can we use the Hexagon data for forecasting. By the way, my name is Chong. I'm an engineer from the marketplace forecasting team. So I'm going to talk about first. Let me show you some examples. Here's one illustration about Uber trip request in San Francisco. In this example, I want to show if you see the different colors, basically red means that we have more requests, and the blue which we have fewer requests. What I really want to show here is that we have different categories of Hexagons. For some Hexagon, we can have lots of requests. For some Hexagon, we may not have, basically we have very few requests. So now let me come to the problem, right? So actually not before the problem, let me talk about a little bit more about Hexagon data. So as Cameron already mentioned, we are moving from this kind of geofence to Hexagon. One of the big advantages is that it's more flexible. Basically, we are going to have very many small Hexagons, and we are going to have our kind of Uber data in the aggregation of small Hexagons. So we can make a very flexible business decision. For example, the price. We can change the price for each Hexagon instead of using one price for the entire city. So because of the Hexagon for the data, we can have thousands of Hexagons. For example, in San Francisco, we have more than 50,000 Hexagons. The problem, as shown in the previous example, is that we can have some Hexagons have lots of data, which is good, but we also have lots of Hexagons. Basically, the data is very sparse. For example, maybe we have a few Hexagons, just have a few requests for the whole day, right? So whenever we have this kind of data sparsity issue for Hexagons, the big problem is that how can we make the decision to be more stable or more solid? Because I'm from the forecasting team, next I'm going to talk about the data sparsity issue, which in the forecasting problem. So for sake of time, I'm not going to get into our detail of the real-time forecasting. Let me just give you a very high-level overview about the problem and how we try to solve the problem. So in Uber, we want to predict the future. We want to predict the future marketplace state. So we can use the future state to help us to at least get us to make the decision in the present. So apparently this is a very classical machine learning problem, right? We want to build prediction models. We want to take in data features to train the model to do the prediction. Some common feature we can use the historical data of the Hexagon. For example, what happened in the last few weeks for this Hexagon. And we also want to use the recent data. Let's say last 60 minutes, how many trips, how many demand, how many supplies in this Hexagon. Besides that, we also want to consider some external signals. For example, we look at maybe there are some events in this Hexagon. Maybe today is holiday. Maybe there are some bad weather like raining or snowstorm, etc. Right? So the basic idea is that we want to use all this data to build our model, to train our model to do the prediction. So now the problem comes. So because we are doing the Hexagon level prediction, if one Hexagon has very sparse data, basically maybe just a few data points in the long history, when we build a model, become very the problem is generally very bad. Think about if there's almost no request for last few days, what are you going to predict for next 60 minutes, right? So this problem has been very hard. So another observation is that what we found is that normally neighboring Hexagons share the similar pattern, right? So if we have one Hexagon, very few trips, maybe there are not many trips in nearby Hexagons. As a result, one solution, what we have been taking is that we try to smooth the data. The basic idea is that how can we use the neighbor Hexagons, the data, the information to consider as the current value of the Hexagon, so that we can use them for building model for prediction. So generally there are two approaches for data smoothing. One is we call the Hex clustering. The basic idea is very simple. We try to first group the Hexagons into clusters, and then what we do for data smoothing, basically we are going to use all the values of the Hexagon in one Hex cluster, make some aggregation, and use the value as the value of the Hexagon we are looking at. So for this approach, the advantage is that we reduce the computation. We have much less data after doing aggregation, right? So it's much easier for us to train the model. It's much easier for us to do the prediction. The trade-off is that the quality of the prediction model will heavily depend on the clustering quality. I think Cameron also talked about the geofence at the beginning, right? So if you do not have a good clustering, basically your prediction can also be affected. Another problem is we may have some neighboring hexagons because they belong to different hex clusters, right? And then we may use different models. As a result, we may find we are having this kind of arbitrary clustering boundary, similar as what's shown in Cameron's talk. We may have this kind of boundaries, just very close neighbors, but they're using different prices. So another approach, because of the disadvantage of the clustering approach, that's why actually a lot of applications in Uber we use this keyring smoothing. So let me use one example to show you what we mean by keyring smoothing. Assume like we have this green hexagon, and we are going to have different layers of neighbors. I just label them with 1, 2, 3. The rough idea is of keyring smoothing is that whenever we look at one hexagon, we also look at all these keyring neighbors. Key can be different values, all the values of the neighbors, and then use the aggregation to some like maybe average or some other dynamic weighting, and then use that value for the green hexagon here. So compared with the clustering approach, right? This approach is much more flexible because we are going to process each hexagon separately. Instead, we have this kind of predefined clustering. Another big advantage is that because of the flexible, there are no arbitrary clustering boundaries, right? We can avoid this kind of boundary issue. So what's the trade-off here? The trade-off is that we are going to have much more computation. Think about like when we, for each hexagon, we are going to take all the neighbors, and in many Uber applications, we may use like keyring maybe 10 or even 20, which means that for each hexagon, we need to aggregate all its neighbor, maybe hundreds of hexagon values. And just look at San Francisco, we may have like more than 50,000 hexagon in total. Think about like we want to do this real-time forecasting, right? Actually, many other real-time applications, which means that for every minute, we need to do lots of computation, do the smoothing. And not only one city, right? Think about like Uber, we have currently we have 700 plus cities in production, right? So adding all of them together is a lot more computation. So in the rest of the talk, I'll be focused a little bit more on how can we have one efficient way to do the keyring smoothing. So I'm going to introduce the Hexagon Convolution approach. Before I talk about the Hexagon Convolution, let me first introduce, at least bring the idea again for the general convolution concept. I'm sure like most of you may be familiar with convolution because convolution is a foundational component for convolution neural network. It's been so popular now. So in case you're still not familiar, let me just use one example to show how the general convolution works. I'm using two-dimensional data to show how it works. So the rough idea for convolution is that assume like we have input matrix. We define a small kernel matrix or filter, maybe just a small matrix. And we want to run the convolution to get the output matrix. So the basic idea is that we want to slide the small or kernel matrix on top of the big matrix. At each position, we are going to do the pairwise multiplication and addition, so like we can get a convolved result. Let me use one example to show it how it works. Assume like we have the green one, which is the kernel matrix, which is a small matrix, and we can slide small matrix on top of this big input matrix. For example, in the blue area, what we do is that we just do the pairwise value multiplication, and then we just do a sum. This is just another example. We just slide the kernel on top of this input matrix. We can get all the convolved result. Of course, there are many details for convolution. I'm not going to get the detail. You can find a lot of tutorial how to do the convolution. So what's the next property for convolution? The next property is that this is highly parallelizable. Another thing that because this is a so common fundamental component of many application or computation, we have lots of material implementation in different packages. For example, we have it in SciPy. Just here a few examples: TensorFlow, PyTorch, etc. Because this is so fundamental, there are lots of optimization have been done to optimize the efficiency of convolution, right? So, and also like we can use GPU to accelerate our computation. So we have this convolution on grid matrix. So the question is how can we do this thing on the Hexagon data? So the idea actually is very similar. What we want to do is that we want to run the convolution on the Hexagon data. Assume like we have input a set of Hexagons. We also want to define our own kernel. This kernel we found like familiar, basically the kind of like our keyring kernel. And we want to run the convolution using the kernel on top of the input matrix, right? So the question is that what's the challenge? What's the challenge? The challenge here is that there are no existing or available package which take in the Hexagon coordinate data. Because most of these kind of convolution packages, they just assume you are going to have this grid matrix or array or tensor, right? So the question for us is that how can we leverage existing convolution implementation so like we can get all the benefit of either the optimization or some GPU acceleration, right? So the next, I'm going to talk about how we're going to do the transformation so like we can leverage existing convolution implementations. Before I talk about how we do the transformation, how we implement the Hexagon convolution, let me first introduce a few Hexagon coordinate system because we need to represent each Hexagon so like we know how we can do the transformation. Here are just a few very commonly used coordinate system. This one is called a cube coordinate. The basic idea is that for each Hexagon, we use three-dimensional data to represent three axes to represent the Hexagon data, basically X, Y, Z. There's some trade-off for this approach. First thing is that we use three-dimensional data to represent two-dimensional data. It's not very memory efficient. Another thing is that we have three values, right? So it's not directly mapping to a grid system. So that's why we are not using this coordinate system. Another coordinate system is called like a double coordinate. I'm not going to get into all the details, but the rough idea is that for each Hexagon, we are using two numbers or two axes to represent. So let's just, theoretically, it's easy to map to a grid square matrix, right? So the question is that after we do the direct mapping, we found like, oh, the neighbors in the Hexagon data may not be direct neighbors in a grid or square grid. So the question, recall like when we run convolution, we normally need a solid error, right? If we have lots of gaps, which means that it's not efficient, and we also do lots of filtering to remove the value that we do not need. So we are also not using this one. This is another coordinate system, which is the axial coordinate. So for this coordinate, we use two numbers to represent for each Hexagon. And the good thing is that after the mapping, we can clearly say like the neighbors in the Hexagon data also roughly neighbors in the grid matrix. And more important, this is a solid error. And we only have a few cells in the corner which we can easily use a filter to filter out. So the approach we have chosen, or the coordinate system we have chosen, basically based on the axial coordinate. Next, let me talk about like how we can use this system to do Hexagon convolution. Now, assume like we have this input data, basically a big input Hexagon data. We also define our own small filter, right? So the first step, what we want to do is that we first use the axial coordinate to represent each Hexagon. After we have this axial coordinate, the next step we do is that we just do the transformation, similar as what we have done for the axial data to map to this grid matrix. After we have this grid matrix, the square grid matrix, things become much easier. We can leverage all these implementations available, right? So we just run convolution on this square grid matrix. We get this convoluted result. After we have this convert the result in grid, the next step is that we can easily map it back to Hexagon data. So far, I just talked about how we want to do the Hexagon convolution. Just try to recall. We have Hexagon data represented in using the H3 library. And then the first step is that we want to use the axial coordinate or something similar. We map to corresponding representation for each Hexagon. And then we do the transformation mapped into this square grid matrix. And then we run the convolution. After we get a convolution result, we just map it back. So next, let me just talk a little bit more about like how we are going to use the Hexagon convolution for this keyring data smoothing, right? So recall like how we do the keyring data smoothing. Rough idea is that we just need, the only thing we need to change is that we just need to set different filters. For example, here I just show some example. The first one is a one ring filter. In this filter, we just use the equal weight. If we use this filter to do this Hexagon convolution, basically means that we are just doing average, just a sum. But beyond that, we can also do this kind of dynamic filters weights, right? So look at the example. By using this filter, essentially we are doing a weighted version of the sum when we do the keyring smoothing. Another thing I want to mention is that when we talk about like the advantage of Hexagon, it's more flexible, right? We want to handle Hexagon separately. So that means that we may want to use different keyring size for different Hexagons. For example, some Hexagon in the city, we may use a small keyring. Some Hexagon in the non-busy area, maybe we want to use a large keyring. So how can we handle this? Actually, the solution is very brute force. Because the Hexagon convolution is so fast, we just run all the keyring smoothing in parallel together, and then we just put the data together. Later, next time we show you like how fast is the Hexagon convolution. Yeah, here's the performance result. So for the performance comparison, we just implement the three basic approach. The first one is the basic implementation. We just, for each Hexagon, we just get neighbors, and then we just do the aggregation or do the sum, do the mean, etc. Another implementation, we use a TensorFlow. It can be any available package, but we chose TensorFlow. We use TensorFlow, implement the Hexagon convolution. We run it on CPU. The third solution is the same code we run on GPU. We can clearly say like by using this TensorFlow implementation of Hexagon convolution, with the GPU, we can achieve almost like 100 times performance improvement. Even with CPU, we still can achieve like a 10 times performance improvement. So to summarize a little bit, I just want to show here that by using this Hexagon convolution, we can dramatically improve our efficiency. Because this kind of data smoothing is so fundamental for many applications, actually this can help us to really reduce the computation bottleneck. So like we can put our more effort on this kind of business logic part. So I talk about like how we can do data smoothing using Hexagon convolution, but actually Hexagon convolution is more than that. Because Hexagon convolution is just a so fundamental component. Think about like in deep learning, right? So convolution neural network has been basically a foundational component for many deep learning network structure. So it's similar like for our forecasting problem. Just recall like for the real-time forecasting problem, what we do is that we try to predict for every Hexagon in the world, for every minute, for next 60 minutes in the future, different quantity. For example, supply, demand, driver waiting time, etc. So the input is our kind of data, historical data, recent data, external signals, and the output is basically our prediction result. So if just look at each Hexagon separately, the big problem is that because of data sparsity, it's very hard to really improve the performance. And here we can clearly use the Hexagon convolution, right? So the first step this is just one neural network structure I'm showing here. For example, we have tried different architectures. In this architecture, so the first step we are going to do is that we are going to run the Hexagon convolution first. Basically, we can aggregate our kind of signal together. And then the aggregate signal will fit into the later part of the deep learning network. For the sake of time, I'm not going to talk about our detail of this network structure, but roughly this network structure was inspired by residual network, where we can increase the network layer, and also it's a lot of ideas borrowed from WaveNet, basically how you can process sequence data. So there's some other interesting part, like in this network, we are not really predicting one value, we are predicting a distribution. I'm not going to talk about our detail, but the rough idea here I want to mention here is by using Hexagon Convolution is such a fundamental component for this deep learning model. And actually it opens us many opportunities, because a lot of, if you look at deep learning literature or research or even industry, just like so many component work built on top of convolution. Before, because we use Hexagon data, it's been very hard for us to do the convolution, a lot of things that we cannot leverage. But now with Hexagon convolution, it's more like opening the door, so like we can leverage a lot of existing work. So with that, let me just briefly summarize the talk. In Uber, we built H3. We built a Hexagon Hexagon aggregation of this Uber business data. We have our kind of data which are aggregated in the Hexagon level, and we also use small Hexagons, which means that we're going to have some busy Hexagon, non-busy Hexagons. Data sparsity can become an issue for us to do to make a solid, stable decision. That's why we need a lot of data smoothing algorithm. And to make this data smoothing more efficient, we built this Hexagon convolution, which really improves the computation cost. By using Hexagon convolution, actually it opens the door for us to do a lot more fancy stuff, building machine learning models, deep learning models. And we are trying to use the Hexagon convolution to build our real-time forecasting model. With that, I would like thank you all to come to talk.